Hello everyone, welcome to a new session of AI Guild. So today we have Tam with us, who is an engineer, algorithm engineer in License. So he's been working around like NLP and computer vision. So we have some really exciting conversation with him going on. So he recently told me about one of his projects, which was developing turntable algorithm, turntable segmentation with like very limited data. So he's going to be talking about the data driven approach. So recent days we have seen a lot of conversation going around using data centric or like data driven approach. Even Andrew Ang has been pushing a lot towards that. So we have something really interesting today. So I hope you guys really like the presentation. And if you have any questions, feel free to put it on chat. Tam is live with us, and we will be answering all the questions through the end of the presentation. So through the presentation, you can put in all your questions. When if you feel like when he's presenting something, you have any conceptual questions or anything around that, so you can just put it in the comments. Also, I will be sharing the link to all the material that Tam is presenting today. You can also reach out to him through email or through LinkedIn. So the floor is for you, Tam. You can just go ahead and share your screen.
Okay. Hello, everyone. Welcome to my presentation. So I will start my presentation now. So you can feel free to leave your question and comment in the chat, and I will read and answer all of them at the end of this presentation. Thank you. Okay. First, a little bit introduction about myself. I'm currently a final year student at the Ho Chi Minh University of Science, and I'm also an algorithm engineer intern at didnt. At here, so I'm very interested in machine learning and especially in computer vision and how to solve computer vision using a data-centric approach. Like instead of using traditional computer vision technique, we let the model learn everything from the data. And I also like doing especially interested in applying machine learning and the research work that bridge the gap between the research, the academic research, and the real world application. So I want to like build a model that we can actually use on in practice and on edge devices. So that's a little bit introduction. So okay, about this talk today. So this talk today, here's the outline of this talk today. I'm going to talk. This consists of 4 parts. The first, the object recognition, is a little bit context about the bigger picture, the whole project that I want to share. And the second is the turntable system, is how we design a system to automate the data collection process for a data-centric approach to problem. And the third is the main part of this presentation today. This is the development process of how a segmentation model, how this segmentation model to integrate with the turntable system that we can use to collect data for the project. And the final one is the key takeaways. This is what I have learned while doing and after finishing, after the reflection of this project. So let's dive in. Okay. The first part I want to share is the recent quote of the creator of the Keras about how we actually do machine learning in what we call applied machine learning. So basically, it was said that in practice, we should spend our resources, your money, your CPU, your time on data collection and annotation and processing the data, and that is where our investment will pay off more than in try to improving the model. So this is what I take very. So this what usually my motto when I'm trying to do machine learning problem. And this presentation today is an example of how we can actually use it in practice. So the first is the object recognition I will put you into the picture of the overall project. So imagine like this. You imagine you want to build a system that can detect and recognize the objects. Detect here means you can detect the object whether or not the object exists on the image, for example, and recognize means, for example, you have different type of the object and which you want to perform the classification, which type of object is. For example, on the image on the right, you can detect this kind of Pokemon and you can classify which Pokemon is it. And we have some a very important requirements that we have to, this kind of model or something that you build have to be deployed, should be deployed on mobile devices like smartphone and tablets. So imagine you want to build an IR application and you want to, so they usually have to work on smartphone or tablet. So you have to they have to be efficient enough to run on those devices. So this is the goal of the project. So we have very two simple and not really simple goals. And so which kind of this goal, what kind of problems that we can have? So the first is for the detection and the recognition. So this is when you think about every possible scenario that you have to detect and classify a toy, for example, like a Pokemon like that, the user might put the toy in very different angle to the front view, the back view, or from side views, or they might use very different lighting condition. For example, the normal room lighting condition, or this is due in a dark room somehow. And the last one, but the most varied one is backgrounds. So you can imagine every kind of background that we have to work on. So this is there are more about the data, but at least the three is most important, and we want to solve it. So for the data variation, and for the model restriction, they have to be lightweight and efficient that to be deployed on mobile devices. So with this kind of problems, when we try to use a data-driven solution to this, we will have some problems. So when people usually refer to data-driven solution, the easy way to do this is you want to collecting more data. So by collecting more data with three kind of data variation, which this means you need to collect for each object, you need to collect images of that object with different angles, different lighting conditions, and especially different backgrounds. So imagine you have n objects and you have n backgrounds, and so you have approximation and n time n images to collect, and perhaps you need to annotate them for the training or testing, for example. And you can take that. Maybe your number of objects is very small because you have a limited amount of objects that you want to detect, but the number of backgrounds is unlimited, and you cannot this solution is not scalable because you cannot repeat every data collection process with every background you add to. So this is the main impediment to the data-driven solution. When people talk about collecting more data, we have to think deeper. It's about how to collect data efficient and how we can process and we can control that kind of data. And another about controlling the data quality, especially when you try to use when you manually collecting the data, usually you cannot control the quality of the image. For example, you can take the image on the phone or you a very professional camera, so the image quality is different. And the quality control is another important factor to take into account too. So with all the kind of problems, our solution is we want to automate the data collection process so we can actually control it, and we can, ideally no human or little human involvement. So back to a very traditional way we collecting data, we manually collecting it. So as I said before, data quality is not controlled. We cannot ensure the data quality, and the reproducibility is hard. Like you give a person, like how you can help me collect this kind of data. So how they can reproduce exactly the lighting and the image quality that you have collected before. So this is the first thing. The second is very time consuming here, of course. And the third one is the scalability issue. So that's why we want to use something called the Turntable Solution. So this is, you can imagine that we can have a rotating table and a camera stick on that, and it can capture the picture of the object here. For example, here we have a ring here, and for this kind of system, the image quality can be controlled. The image and the lighting condition is, you can control everything. Okay, so this is very good for quality control. A little human involvement, I mean, you may only need to place the object on the table and start the system, and then the system will automatically collect all the data for you. The scalable is very good. You can add more cameras to capture more images, and also you can scale the system itself, more camera, more turntable, and you can do it parallelly. So you can collecting a large amount of data in very short amount of time. But this system have a very cannot solve the last one. The biggest problem we have is the background data variation. As you can see on the picture, it's very difficult to change the background of the turntable system. For example, you can change the background to some material, the color, but how you can put a background like a coffee table background on this turntable system, I think it's very hard. So the most disadvantage of the system is a limited background that we can record. So how do we actually solve it? I think this is very not very so smart solution. I think anyone can come up with this kind of solution if you have now a field something like segmentation. So what we proposed is, from the turntable image, we're gonna do the segmentation and the mapping. For example, here you can see it kind of remove everything, the background, the turntable background, and then when we add the new background, we can blend the segmentation and mapping image with the new background, and we kind of have a brand new background image here. It's not like 100% natural, but I think it's gonna be good for your training data. So you have more background. So for this solution, then this solution can solve the background variation problem, because for this you can collect the background independently from the object itself, and by doing that we can need to collect and background and objects, and then we have and square images. So it's very easy to do this, and also you can, and for the background quality, we do not need to make this very high quality. So you can record this kind of background image by mobile phones or something. So this is the solution that we propose to solve the background limitation. So as you can see, the main component of this solution here is we need to develop a segmentation and a mapping model. So the most, because here we have two models, but in this talk we only focus on the segmentation, because it's very important role on the this component, because unless you have a very good segmentation match, in this case you have the good mapping result. Otherwise, if your segmentation match is very bad, so the mapping model, I think, can't help too much. So this lead to the third part, which is the main part of this presentation, is the process of developing the segmentation model. So this is like how this is literally how I developed this. So the first thing in mind when you try to working on a machine learning problem, or I think any kind of problem, is define your goal. So by defining your goal, I mean you have a goal and a specific target you want to achieve, and ideally it should be reflected by some metrics that you use here. For example, I have two goals for this segmentation model. The first one is the segmentation performance should be very high to preserve the detail of the object. So you want to first, you don't want to the segmentation mask to cut some part of the object. Otherwise, it's very weird. So you're gonna introduce very weird object in your data set. And the second, you also don't want to include too much false positive, which means too much redundant background is a match. Otherwise, your matching is not gonna work because unless you can remove the background, then you actually can blend the background into it. Otherwise, it doesn't work. And just two of those requirements are reflected by some metric here. This is the IOU, the intersection of a union, which is used very common in segmentation problem. And the second is just the recall. So we want to achieve very high recall. We want to preserve the object. And also we want it to work with different turntable background in case I will talk to it in detail later why we have to have this goal and unsync the categories. I will talk to this later. And the second requirement here is it should be very efficient. Not really very efficient, but efficient enough so that our data collecting process it should not affect our data data collecting process. It shouldn't be an impediment to this. So it's not need to very fast, but it should work fast enough so that we can collect the data and let it run for like a few hours. And then we have a new data. It should be good. So when I try to solve this, here is the some of the problems that I encounter. The first one is we usually cannot find the public open data set for a specific object that we want to segmentation or to perform the segmentation. And this means the ground truth for the segment data is not available for you. So usually manual labeling the segmentation mask is not an appropriate solution because, as you know, segmentation labeling is very time consuming. For example, for a simple segmentation, it can take up to 1 minute per image. And so it's like if you have like 1,000 images, so it's going to take a lot of time to annotate this. And so how we actually solve this kind of problem. So for the limited data problem, so you can think that, okay, we might use some external background removal service. You have something like remove.bg or something. So you can remove it. So for this kind of solution, you have to think about two things. The first is your budget. So can you use do the segmentation for all of your data, or you can use. So usually in normal cases, we usually cannot have the budget to run for all of our data. So usually we cannot run for all of our categories of objects. We mean sometimes you create a new toy, you want to add a new Pokemon in your app, and then if you have to do all of this again. So just usually you cannot do for all your toys. And the second is the data quality, because they also just a service, not labeling. So you cannot expect that the ground truth is perfect. So you have not to accept that the ground truth is only adequate. So in short, we have both limitation in the quantity of the data and the quality of the data, the number of data sample and the quality is ground truth. So with this kind of problem, here is how I developed the model to study. So the first model I want to try to tackle this problem is a martial arts and Improv model. So as you probably know, the martial arts CNN is the kind of instant segmentation model. It can perform the detection and the segmentation of the detected box at the same time. And that's one of the reasons why we choose the martial arts CNN. And the second is we want to leverage the detection dataset because usually we have a very large amount of detection dataset and it's more accessible to than the segmentation data. And with that in mind, I quickly train a martial arts CNN model and evaluate the results on our data to get the insight about the possible issues that we actually encounter and propose solution to solve it. This is very important. You always need to have some baseline model or something to quickly to see the result, how it's performing and what kind of issue you have. Otherwise, you're gonna solve a problem that you don't understand. And I think this is not a good way to tackle any problem. So after doing that, these are 4 issues that I found. The first one is the bad ground truth quality in both training and testing data. So for training data, the bad ground truth quality gonna affect how the model learn, and for testing data, it's gonna affect how you evaluate the performance of the model. It doesn't truly reflect the performance of the model. So it's when you try to comparing different models, then it's very confused. So that's why we need to spend time to clean the ground truth quality of the both training and test set. The second one is the prediction box affects the segmentation result. So as you know, if you use the instant segmentation like martial arts CNN, it will detect the box first, then it performs the segmentation. So if the box is not correct, so you cannot expect that the segmentation result is correct. So this is the second problem. The third problem is a false positive problem that usually you have redundant pixel around the object. And for some part in the object, for example, for some object, you have a hole inside and you want the mask to please don't cover this part. Then you got false positive. And the last one is a false negative. Usually when you have the similarity in the color of the object and the background, then maybe the mask is not good and it cut out some part of the object. So how we solve each of these problems? Okay, here are some example images of that kind of issue that I mentioned. The first on the left, you can see the prediction box issue, which means for example, in this case, when you doing the prediction box wrong, then you're gonna miss this part in the segmentation process. And the second is on the right side is a false positive. So usually it's not virtual, but you can imagine that we have very border around the objects like this, and usually we don't want to include that into our result too. So this is how we actually solve it. For the background truth, I think it's very simple, but it's gonna be time consuming, but I think it will pay off. So you don't need to re-annotate the whole data set. You only need to find very background truth and re-annotate one. And I think it's more efficient than doing on the whole data set because the model can generalize, so my ground truth is adequate enough for the model. It doesn't need to be very perfect. And for the prediction box issue and the false negative, so this is kind of the model architecture issue. So maybe a way that we can tackle this is try different model, and what I propose here, we use semantic segmentation model. I will talk to it later. And the last one is the for positive. This is just the way we use the system. Maybe we just try to change the background. For example, if you have a white object, you might want to use a black background instead of the white background. So there's no more confusion for the model. So with that in mind, we have, so in short, we have our first baseline model max RCNN, and we have some issue. And the first and the fourth one is not related to the model, but we propose that we try to use the second one. We try to change to the semantic segmentation model. So this leads to the next part. This is another. This is one of the semantic segmentation model. The deep levelity first. So why we choose this? First, we want to, like I said, decoupling the detection and segmentation. So we want to train a separate detection model, and then we use that kind of input, the cropped image, to input to the segmentation model, so we can achieve the best result. And the second is the semantic segmentation. Usually for semantic segmentation, you want to achieve very like a pixel level accuracy. So this kind of model are designed to work to achieve pixel level accuracy. So they are likely to have better results compared to the semantic segmentation instant segmentation one. And the last one is it's very efficient. Yeah, not efficient enough to run on edge devices, but very efficient if you run on the CPU. Yeah. So yeah, so I kind of repeat that previous process. I try to use this kind of model and train the data and analyze the result to see can we actually solve the issue. So while I found that it kind of resolved the false positive issue and the prediction box covering issue, it has another issue. It's the generalization. It's like this. The performance of the model on white background data, which exists in the training data, is very good. But on other background, like for example, black, green, which doesn't exist in the training data, is very bad. So this indicates that the model is overfitting with the data we have. So again, data collection comes to rescue. But we can, again, this kind of solution is not scalable again. So if we want to collecting new training data for every background that we use in the future, so we need to like do it over and over again. But this is not what we want to achieve. Instead, we want to the model to not very high performance, but a decent performance on unseen or even unseen backgrounds. But then, if we have to collect the new data, it should be very quick and easy to do so instead of have to do all the data collection all over again. So here to resolve this background issue, we actually use the same way that we use to resolve the background issue for the detection model, which is the background augmentation here. So similar to the way we augment the data for detection training, we can use the same technique, because now we have the mask of the data, you can take the object out of its background and then blend it to a new background. So it's pretty much pretty similar to the way we did before. The second thing I found that very helpful is, even though it's not directly related to our problem, but we use some salient object detection data. For this data, so this data is it's gonna label the most visual attractive object in an image. And you see in our case, the turntable system, usually our object that we want to try to capture the image is the most visual object. So actually, we think that this kind of data can benefit the model. So instead of trying to acquire segmentation data, we're going to use this data as a starting point for the model, and then we're going to train them at our segmentation data later. So this is what I have done. I trained the segmentation model with the salient object detection data first and use it as the pre-trained way to train with the object segmentation data. Also, this is the first one, and the second solution is the background augmentation. I collect the background image of the turntable backgrounds, only background image, and apply on-display background replacement, so we can have our training data the segmentation image with a completely new background. And if we try to achieve the best of the both worlds, we can both. If you can do this, you can do it's both. You can collect both new training segmentation data, and you can also collect the augmentation data. I think it's work to get the best of the both worlds, of course. So for this, for this kind of issues, then we successfully deploy a segmentation model that can work with unseen background. And whenever you try to use a new background, we only need to take like a few images, like 100 images of that kind of background, and just fine tune it again, and it works perfectly on the new background. So this kind of solution is very scalable because you can work with, even though the model cannot work with all the background that you possibly use, but it's very easy to fine tune the model. So this comes to the next part of what I want to deliver is the key takeaways. Or here, here is the Easter egg of this presentation. So I didn't list it in the outline. So usually, when I talk to the two previous parts, so people seem to think like, okay, it seems like everything you try, it just work, but in reality, it's the opposite. It's usually reality opposite disappointing. So I want to mention all the failures that I have on the way, because these are what I have tried and found that they didn't have to resolve the issue, but I believe they should be also be credited as equally as what work, because anyways they taught us something, like Edison when he invented the light, he just say he found just 1,000 ways that this didn't work. So what didn't work here, I think this is very important because in the future you might want to avoid this. What didn't work here is I'm trying to use different state-of-the-art segmentation models, and I found the performance is kind of similar. I tried very sophisticated laws that are proposed to to optimize directly the IOU matrix, but I found that this kind of loss is very hard to use, and it's very you have to spend so much time fine-tuning to get like a decent result with kind of loss. And I tried different training optimizer and learning schedulers, but you can. I think the best way is just go Adam and tree, and you just go to fixed number. It doesn't have. And finally, I tried very different augmentation method. I remember that I found a very very helpful article on the Kaggle that mentioned all the techniques that used for segmentation problem in the competition. I tried mostly like 70 or 80% of them, and I found that I only found ones that work with the background replacement. All the kind of augmentation, it doesn't make they don't make sense. So this is what didn't work. And usually you have this. Usually you have more failures. There's just a sixth one here. So okay, this is the final. The final part of this presentation is the key takeaways what I have learned on the way. I think you also interested in this. The first one is you need to work towards the goals with the eyes on the data. This means for the goal, you have to have in mind about what goals you want to achieve, what issue you want to resolve, and you have to understand and use appropriate metrics that reflect the goals that you want to achieve. This is very important. Otherwise, you just wandering around and you endlessly working. It's not good. And for with the eyes on the data, which this means to understand and spend your resource on data collecting, annotation, cleaning, augmentation, they are likely to pay off sooner than trying to improve the model because we have to admit that all of them we cannot like create a new model for every project that we use, and usually we can most of us are not capable of doing that anyway. So working on the data is like the most efficient and effective way that you want to try to improve the model. And usually the problem does not lie in the model, it usually lie on your data. And the second is state-of-the-art has diminishing return. Trying state-of-the-art model is fun and it's very tempting to do so, but keep in mind that it's reasonable to use good backbone and architecture, but you need to be aware that the improvement, usually 1 or 2% improvement on one dataset, might not generalize on different datasets, especially your dataset. So usually they only test the model on very famous dataset like ImageNet or Coco or VOC or something like that. And it's not guaranteed that it's have improvement on your dataset. And usually when you see the improvement is not significant, then chances are they won't work on your data too. So trying is fun, but you know, you have to resist attempting to just change the model and hope it work. And the third one is augmentation is helpful, but you need to be selective. It's kind of like you cannot apply every augmentation method on any kind of data you're working on. First, you need to understand your data and see whether it's reasonable to use a specific augmentation method for your data. Does it make sense? Does your kind of image after being augmented really like exist in your training data, or just some kind of weird image and gonna confuse the model? So be aware of that. And the final one is you need to have a good code base and tools to make the machine learning iteration faster. The machine learning iteration, which means you try a model, you evaluate, you analyze the result, and you file issue, and you propose the solution to tackle to resolve kind of those issues. So to do that efficient and faster, you have a good code base and tools that you make sure that all your experiment is reproducible and or something like that. So for example, usually when I'm working on, for example, on PyTorch, I usually start with the PyTorch lining, or for example, if you work on specific computer vision problem like detection or segmentation, so the open MM lab is not the repo you want to check out because they provide a very good code base that you can work on, and it makes your work much more easier. And the last one is reflection. So usually after finishing a project, you should reflect like what I have done here, to see what works and what didn't, and to avoid to find a way to spend your resource in, especially your time, more efficient in the future. That what you want to try first. So, okay, this kind of as my presentation today, and you can find me at my email or my link in here. And if for now, if you have any questions, just feel free to put in the chat. So I
Hi,
think
that
I
was an amazing presentation. Like, it was a very, very insightful presentation. I'm someone who's not worked a lot on computer vision. So for me, it was a lot. It was very, very interesting, especially the parts. Like, I really loved the section that you have added a section about failures on what might go wrong. That's sometimes so important because the kind of data sets that we get online, like the open source or the free source data set, they do not technically represent the real world data, right? And that's where we do face a lot of issues on how these algorithms are working on these data and if they are actually being effectively processing the right information. So it was very insightful to add that section, and I feel like it's very important. It's a takeaway for me that I'm going to be like telling all my future speakers and like even my teammates that having that failure section added to your presentation is super important. So thank you so much on that. I'll let the screen be as it is so that people can just like note your email address and LinkedIn. I would definitely be sharing the same information in the description of the video that goes on YouTube later on. So for some of the people who have been putting on the chat that if the session is recorded, yes, the session is recorded. You can find it on the YouTube channel. So I will be posting that link as well. So you'll find this entire session recorded and all the information on the description below, all the slides that Tam has used, his LinkedIn, his email, etc. So I will be doing that soon. In the meanwhile, Dan, I had a few questions for you. So I think like
uh,
some of the questions came from. Can you hear me?
yes.
Okay, perfect. So some of the questions came from the chat. So one of the person had asked about how eliminating background for an image will solve the problem when you're actually trying to potentially lose some of the data while eliminating the background.
So let me repeat the question. So it's like how eliminating the bad example can actually help the model training, the model learning.
Yeah, yeah.
Yes. So usually like this. So usually you have to think about how much bad example as a proportion of your training data. For example, like you have like 100,000 images, then you have like 1,000 bad images. It's fine, but well, for segmentation data, usually we don't have the kind of luxury. We only have like 1,000 or 2,000 images, and like 100 images, and especially when it happened for a particular class type of object, then if it's going to affect the model, then not, it's confused for that specific class. So you in that case you want to eliminate the bad example, and that's why I also emphasize that you don't need to eliminate or re-annotate all of your training data because I think it's not that, but you only need to find the one that caused the most problem to your training data and want to eliminate them.
Yeah, that makes sense. That makes sense. So I hope your question is clarified, Mohammed. So a few other questions is like when you are talking about like eliminating such background information from the images, what could be the possible like real world use cases that you can see here? Like where could it be very effective, and where which are the cases where you might not want to do something like that?
So it's the background uh, displacement and background augmentation.
Mhm.
Uh, so so I think it's very specific to your kind of issue you have. For example, in this example here, I have the issue with the background variation. We found that the model like doesn't work well with the unseen background, and then this is the main drive for our technique here. So this is the one that causes the most problem is okay, we don't have enough background variation, and we cannot like collect all the background. So how we can separate the two process? We can process collect the object independently from the background, and then we can produce very large amount of data. this is the way that we resolve the issue. Just, I think this kind of technique can be generalized somehow, but I think it just depends. It very depends on what kind of issue that you have. So you have to understand the kind of issue you have. Then I think you will come up with a solution. I don't usually work the other way around. I don't think we can just take every solution and apply to our problem. Usually, I found that that's not effective.
Yeah, that makes sense. So one of the other questions I was just curious about. So Jenny had commented that she's also working on something similar using Yolo version 5 for object detection. So is that something you have already tried?
So for Yolo detection, I think it's very like getting present right now. Yolo is very famous one, but I found that when think about detection problem, detection model, I usually like refrain myself from using that because first, the reproducibility is kind of not as good. It's like you usually cannot, just training process of the Yolo model is very complicated, and somehow if you can imagine in what case you train the model, then another college of you take up your job and this part of project and think about how you're gonna document the whole training process and let that person can reproduce that experiment. I think that's one of the one factor when I think about which model I should use. And also, it should be very like another requirements that I put in the slide. It has to be deployable on the mobile and edge device, and it should be integrated into the current system that you are using. So you have to take that into consideration when choosing the model, because as I think, all kind of models gonna work like fine. Just like they're not very bad. For example, you can take the Yolo or you can take the Mars, the Mars or CNN or something. I think they both perform on anything that is fine. Just don't like too focus on the magic on the code data set. They don't reflect everything usually when you work on your data.
Yeah, that makes sense. That's probably one of the things I even thought of. Like models are very subjective. So one other question is also like similar to what we had earlier. That what was your experience with UNet and image segmentation apart from using like mask recurrent neural networks and Deep Lab version 3?
So so apparently, usually when unless so for now we kind of like when we achieve our targets, then we usually stop there, and the next part of this is try to finalize everything. By finalize, I mean you have to document your code. You have to write document the training model, so everything that I think, so that also people can actually use it and reproduce it, and you also like exporting the model so that also people can just uh, use, for example, your Docker image, and then they can use it instead of have to install every dependency that you use. So I think the final part of that is try to document everything, but I think it's kind of related to the engineering part. So I think it's important too, but usually I don't include it to my presentation because it's not the main topic.
Got it. Makes sense. Another question, I just found this thing in your presentation that you were talking about augmentation methods, right? Like how do you augment the data? So when you have like multiple different ways of augmenting information or like image data, especially, how do you select the best one? Because that's something which is not really a supervised approach. So how do you understand
Yeah.
the metric in an augmentation method, and how do you select the right one?
So, so usually for the augmentation, usually you don't find many papers talking about that. And I think this is very like depending on your data. So you need to first understand your data first. What kind of data are you working on? For example, you're working on some medical images. So like for example, the X-ray image, then maybe you found something like random crop. So random crop is used very like most or every model training they use random crop, but you have to think, okay, if you random crop or rotate or flip your images, this makes sense. For example, you want to detect the people heart or something like that. It doesn't make sense to flip the image so your heart is on the right.
Yeah.
So it's like you need to like put it on the table. Okay, if I apply this to this kind of image, this makes sense. And for example, for something like for X-ray image, usually when you have like black and white background and you do some rotation, so you can think that when you do some rotation, you have some pixel you have to fill the value in because when you rotate, you're gonna miss some part. Then you can have to think, okay, what kind of value should I fill in this, black or white or something? So you have to think about it, like the way you think about the model. Just don't like blindly apply anything you have, because usually I found that the augmentation is very easy to add in your training code. It's just because they're very well spotted. You just need to add a few lines of code, so it's very tempting to do that. But it's just to resist the temptation. Okay, think first, because as a file, the time you spend on waiting the model to training is long, pretty much longer than the time you can think about it.
Absolutely. And one of the other things, like probably the last question I have for you. So you were mentioning about, having the right kind of tools for you to have this machine learning iteration going on, because when it comes to, testing these models, it does take a lot of effort, because every time you have like a new research paper, you want to try a new state of the art model, you have a different technique, the entire pipeline of like doing the data processing, putting it into the training, validation, and cross validation, and all that entire pipeline does take a lot of time. And how do you do this in an iterative process is in a very less time consuming manner. You have to have the right tools for that. So what are some of the tools that you use? Like what is something that has, like reduced your time span in doing this iteration and like testing out multiple models?
Yeah, so for the tools, for now, you can find like different kind of tools to manage your experiment.
Mhm.
They are very sophisticated and then they can help you match it so easily. But I think I'm kind of do a very traditional way. I just think first I just put every experiment in a folder, and for each folder, each folder is a model, and for each sub in that folder, I have like run from 1 to 10, for example. And for each of the run, when I try to run the model, I always try to like keep like a verse image, like I try to cache everything at the time I'm running the model, like to configure everything. I want to make sure that, because usually I found that after like 10 experiments, you gotta forget about what the first experiment you're doing. So sure to keep everything necessary to understand that experiment in just kind of folder where you can find it. And usually I do that. I put everything in that folder. That later, if I forgot, I just need to read the file and understand what I'm doing here. Sometimes I put a little command on the file to say, okay, I want to run this because I want to test this, and yeah, and then you like another making application to take note everything. I think this is the easiest way that you can do it without the help of any tool. So you have to be like, I think it's like being careful is like less time consuming, like making mess clean it later. Usually, I remember when I first doing machine learning, I making all the mess, and sometimes I have to like, oh god, I forgot to calculate. How can I reproduce this? And later, for now, I always try to stay organized at the beginning of the project. And one interesting that you can do that while waiting for the model. You see what I do when I'm waiting for the model for training.
That's funny. Yeah, I mean this was like really informative, like something new. Like I have not heard about like turntable segmentation, not something I've used. So this was really interesting. And so one of the reasons, Tam, I'm doing this AI Guild sessions is to help people understand, okay, what are the real world use cases that you're going to tackle when you are moving into the operations part of it. So when we are in school, when we are learning this theoretical part of it, it's very different. When what you learn in books, what you learn in courses is very different on how things are being applicable in real world. What kind of data are you tackling with? What kind of failures that you mentioned in the presentation that you can face when you are developing these algorithms. It's really important to give a reality check on, so this is how it looks like, so this is how you progress with a machine learning problem, this is how the data looks like, these are the challenges which you might face, and like this is a right approach to solve these things. So this is one of the reasons I have started this AI Guild series, that people can learn from experts like you who have worked on such problems and understand how does the entire pipeline function. So if you guys are watching and you like the video, like please do follow the AI Guide series, because we'll have more and more such videos where we'll talk about real world use cases, and you'll see in practice how do like data scientists and machine learning engineers actually tackle with these day-to-day issues, and what are the right kind of tools and methodologies they use, and what's the pipeline they follow basically. So this is more towards as close as real world applications as you can see in data science and machine learning. So once you have gotten your foundations ready and mathematics, statistics, and you do know about like data science and machine learning algorithms from a theoretical perspective, it's very important for you to understand how does it work in practice. So do follow the AI Guild series. We'll be coming up with more use cases, more challenges, more such applications, and yeah, you'll learn from all the people on how they have actually built the solutions. So great.
Okay.
Thank you so much, Tam. I really appreciate you taking out time at this. I know it's pretty late for you. So thank you so much for doing that. And yeah, I think I will be sharing all the material that you shared with us.
Yeah. So thank you for the invitation and having me today. It's nice to share to do the reflection on my project and share with other people.
It's a
Feel
great
free to
feeling.
contact me if any of you have any questions. Yeah, you can
Yeah,
contact my
absolutely. So
email or
you
my.
can see his contact on the screen. I will also be sharing the same thing in the description of the video. So
Yeah.
either way, you can find his contact.
Yeah. Thank you.
Great, great. Thank you so much, Tam. Have a good one.